If coding problems feel overwhelming or confused, you are not alone. And you've probably asked yourself which data structures and algorithm topics are actually worth studying. Most tech companies ask the same 8 data structure and algorithms patterns over and over again in their interviews, and if you understand those concepts deeply, you're already ahead of 90% of candidates. Hi friends, I'm Maddie. I'm a senior software engineer who previously worked at Google and internet other big tech companies like Amazon, IBM, and Microsoft. I've been down the internet gauntlet at multiple companies, and today I'm breaking down the 8 essential data structure and algorithms concepts you should master with tangible example problems. By the end of this video, you'll understand exactly which data structures matter most, how they're tested in technical interviews, and the specific problems you need to practice. Let's get right into it. Before we even touch data structures, you need to understand Big O notation because interviewers will ask you to analyze your solution's efficiency every single time. Big O measures how your algorithm scales as input size grows. Think of it like searching time. If I already know my phone's charging from the wall outlet and need to grab it from there, that's O of 1 constant time. It doesn't matter how many items are in my room. But if I'm searching for a specific book on my bookshelf by checking each one, that's O of n linear time, where n is the number of books. In terms of interviews, O of 1 is constant and ideal but doesn't appear very often. O of log n is very efficient like binary search. O of n is acceptable for most problems, and O of n log n is what you get with efficient sorting, and O of n squared or worse usually means you probably need to optimize more. Interviewers love asking what is the time and space complexity of your solution after you solve a problem. For example, if you're solving the classic two-sum problem, finding two numbers that add up to a target, the naive approach, checking each pair, is O of n squared. But using a hash map gets you O of n. You should always be thinking about time and space trade-offs. Sometimes, using extra memory with something like a hash map gives you faster runtime, and interviewers want to hear you articulate those decisions. Now that we understand time and space complexity, let's talk about our first data structure, arrays. An array stores elements at contiguous memory locations with O of 1 access by index, but inserting or deleting in the middle takes O of n because you need to shift elements. Interviewers might ask you to do array operations in place to test space complexity awareness. When they say things like reverse a string in place or rotate an array, they're checking if you understand how to manipulate arrays without allocating new memory. In order to master arrays, get comfortable with array traversal patterns, forward and backward iteration, two-pointer technique, and sliding window. These patterns appear everywhere in coding interviews. Next, let's talk about hash maps. A hash map stores key value pairs with an average O of 1 insertion, deletion, and lookup by using a hash function to compute where the item should go. Think of a hash map like a code check, where instead of searching through a massive pile of codes to find yours, you instead present a unique ticket, the key, and the attendant instantly goes to the specific hook, the index, where your item is stored. For example, let's rehash the classic two-sum problem we talked about earlier. Again, you're given an array and a target sum, and you need to find two numbers in that array that add up to the target. The hash map solution iterates through the array once, storing each number, and checks if the target minus the current number exists in your map. That is O of n time versus the O of n squared for the brute force approach. Here's another classic interview scenario. Design a file system with create path and get methods. This appears in some actual tech interviews, and the optimal solution uses a hash map to store paths as keys with their values. The interviewer might then ask you to extend it with additional operations like listing directories or adding content to files, testing your ability to build on top of your data structure choices. Something else you should keep in mind is how hash collisions work and how best to resolve them. When two keys hash to the same location, most implementations use chaining, storing multiple values in a linked list at that index. This is why hash map operations are O of 1 on average, but can degrade to O of n in the worst case with many collisions. So the bottom line is that whenever you need fast lookups or need to track frequency or existence of elements, think of a hash map first. Now let's talk about sets. Sets are like hash maps but only store keys without values, maintaining uniqueness with O of 1 average case operations. Interviewers use sets to test whether you recognize patterns around uniqueness and membership. Common interview questions that you can use sets to answer are ones like remove duplicates from an array. A set gives you automatic deduplication. Find intersection of two arrays. Add one array to a set and iterate the other, checking membership. Detect if a linked list has a cycle. Track visited nodes in a set. The trick with sets is that they're often not the main solution but a supporting data structure. Interviewers might have you use a set alongside another structure like a graph for marking visited nodes during BFS or DFS traversal. Now let's talk about linked lists. Linked lists store data as nodes where each node contains a value and a pointer to the next node. Unlike arrays, linked lists don't give you O of 1 access by index. You have to traverse from the head. But inserting or deleting nodes is O of 1 if you have a pointer to the right location. Classic linked list interview questions include ones like reverse a linked list. This tests pointer manipulation and whether you can think iteratively or recursively. Detect a cycle in a linked list. This checks if you know the two-pointer technique using slow and fast pointers. Merge two sorted linked lists, testing your ability to manipulate pointers while maintaining sorted orders. You might even encounter linked lists in your classic design an LRU or least recently used cache system design question. This uses both a hash map like we talked about previously and a doubly linked list. The hash map gives you O1 lookup while the linked list maintains the order of recently used items. When you access an item, you move it to the front of the list. When the cache is full and you need to add a new item, you remove it from the tail. The next important data structures to cover are stacks and queues. Stacks are last in, first out. Think of a stack of plates where you can only add or remove from the top. Queues, on the other hand, are first in, first out, like a line or a queue at a coffee shop. Both give you O1 insertion and deletion. A classic interview question that you'll need a stack for is the valid parentheses question. Checking if brackets are balanced is a perfect stack problem. Every opening bracket gets pushed, every closing bracket should then match the top of your stack. Stacks appear constantly in problems involving parsing, matching, or tracking previous states. Anytime you see a problem where you need to process elements in reverse order or track the most recent item, think stack. Queues, on the other hand, show up in breadth first search, which is huge for interviews involving trees and graphs. When you're doing level order traversal of a tree or finding the shortest path in an unweighted graph, you're using a queue to process nodes level by level. So speaking of trees, what exactly are they? Trees are data structures that organize data hierarchically with nodes and parent-child relationships. Binary search trees are trees with a special property. The left child is always smaller than the parent, and the right child is always larger. This gives you O of log and search, insertion, and deletion for balanced trees. Common tree interview questions are ones like, validate if a tree is a valid binary search tree. This tests whether you can think recursively and maintain constraints as you traverse down. Find the lowest common ancestor of two nodes is another classic. And finally, in order, pre-order, and post-order tree traversals. Interviewers want to know if you can traverse those trees iteratively or recursively. And finally, let's talk about heaps and another type of queue, priority queues. Heaps are complete binary trees where parent nodes are always greater in a max heap or smaller in a min heap than their children. Priority queues are typically implemented with heaps and give you O of log and insertion and deletion with O of 1 access to the min or max element. Think of a priority queue like a hospital emergency room. Instead of treating patients in the same order they arrive, the most critical case is always seen first. New patients are assigned a triage score, and the ER continuously maintains the ordering so that the most urgent case always rises to the top of the queue. Classic heap patterns include questions like find the kth largest element in an array. The naive approach sorts the array with O of n log n time complexity, but using a min heap of size k gives you O of n log k, which is fast for large arrays of small k. And there you have it. These are the top 8 data structures and algorithms concepts you should know to ace your interviews. Data notation, arrays, hash maps, sets, linked lists, stacks and queues, trees, and heaps and priority queues. The trick isn't just knowing what each structure is, it's recognizing which one solves a problem effectively and being able to articulate why. Hope this video is helpful, and if you enjoyed it, please hit that like button and subscribe to my channel for more tech walkthroughs. Thanks for watching, and I'll see you in the next one.